Located 963 feet underground at the Nevada National Security Site, the principal underground laboratory for subcritical experimentation, or PULSE, is the prime location to conduct large-scale subcritical experiments. One of the key diagnostics that the ZEUS testbed will house is the Neutron Diagnosed Subcritical Experiment, or NDSE. This new diagnostic tool supports the ability to make prompt reactivity measurements of the dynamic experiment. This enables us, for the first time since the cessation of underground testing, to assess the nuclear performance of a given system. Key components of the NDSE system are the pulsed neutron generator, the collimation elements, the gamma detector array, and the recording system. The pulsed neutron source that enables the NDSE diagnostic is the ZEUS Dense Plasma Focus, or DPF. To prepare the system for firing, capacitors are charged to a specific voltage and then discharged at a precise time during the experiment. Once the trigger signal arrives at the DPF generator, a plasma sheath is formed within the vacuum chamber. Magnetic forces then push the plasma sheath up and ultimately inward onto the DPF anode. As the sheath collides with itself, it compresses the deuterium-tritium fuel, causing nuclear fusion. The fusion reaction creates an intense burst of high-energy neutrons. While the 14 MeV neutrons are emitted in all directions, only the collimated neutrons, shown here, pass through the collimation and shielding elements. The interactions of the high-energy neutrons with the fissile material generate both neutrons, shown in blue, and gamma-scattered rays, shown in green. The collimation elements narrowed the beam, allowing only select gamma rays to travel towards the detector array. The collimated gamma rays, now traveling at the speed of light, are followed closely by the slower-moving neutrons. Once the high-energy gamma rays reach the detector array, they are converted to light photons within the scintillating element. These light photons are amplified and converted to an electrical signal and transmitted to the recording system. Soon after, the slower-traveling neutrons impact the detector wall and impart energy into the scintillating elements as well. Once this happens, the window for the NDSE measurement has now closed. The data is collected and then analyzed. The resulting slope of the recorded signal is a direct measurement of the reactivity of the system. A more horizontal slope indicates a higher peak reactivity. The data collected through the NDSE measurement technique will aid in the assessment of the nation's aging nuclear stockpile.